Hello and welcome. This is the next question for AQA AS Physics. This is the January 2009 paper. Okay, so in this question, kind of drawn the diagram on the board for you there. It's a Feynman diagram. Sorry, and essentially it is an electron and an electron coming together and colliding. Okay. And for part 3A part 1 says state the type of interaction involved and name the exchange particle. Okay, so it's obviously worth 2 marks. Now, what I would like to mention here is I did do a video, I'm not sure it's up yet, which pretty much goes through everything on... Right, so sorry about that, I'm not exactly sure what happened. I think the camera probably just had enough and cut out. Okay, so anyway, I was saying that for 3A, it's asking for what the virtual exchange particle is. Well, because it's an electron, and basically it's not decaying, okay? So the interaction is not weak, therefore the interaction must be to do with electromagnetism, and the exchange particle that has is a virtual photon. Okay, so that's 3A. Sorry, second. Right, okay, so that's 3A as it says. 3A part 2 says state 2 other quantities other than energy and momentum that are conserved in this interaction. So for this, obviously, we need to relate to our conservation laws. Now, there are many conservation laws, and obviously we can't use energy and momentum. Okay, so potentially another one that is also conserved. Sorry, double checking. Is you can have any one from charge, mass, lepton number, baryon number, or strangeness. Personally, I would go with charge and mass. But as I say, it's totally up to you. Okay, so say B, I put charge and mass. It's only asking for 2, so you could do 3. Waste a bit more of your time if you wanted to. 3B part 2. Sorry, 3. What? Oh, sorry, 3A part 2. God, shows how much of a long day it's been. It's not even started yet. Okay, so that's 3A part 2. 3B is another type of interaction. Okay, so basically this is I'll just kind of copy it out for you. So we've got a proton coming in and an unknown particle going out and an unknown exchange particle. Okay, we've got an electron there and another unknown particle coming out. Okay, so it says complete the diagram to show 2 particles formed in the interaction and the exchange particle. Well, I mean, it is quite maybe sort of hard to spot here because we've got an unknown exchange particle and an unknown particle here if you haven't properly revised your Feynman diagrams. Now, straight away that says to me, well, what Feynman diagram have we got that relates the proton and the electron? Well, I personally can't think of any, but it's definitely, off the top of my head, it's definitely not some kind of decay because it's got 2 going in at the same time. It's definitely not some beta plus or beta minus decay because we'd have, well, it doesn't look like that, okay? Is it, well, it's definitely not this one. We've just done that in terms of the repulsion. So the only other one you should be aware of, just kind of a method of cancelling down really, I suppose, is the electron capture. Now the electron capture, whereas a proton turns into a neutron, and the electron, basically inner shell electron, an outer shell electron collides with an inner shell electron, okay, and it's kind of almost absorbed in, think of it like that, so you have an electron going in, and then we have a electron neutrino going out, okay, and now because it's pointing this way, the arrow, okay, so on your diagram it's kind of pointing from the proton to the electron. That means the proton goes in first and then the electron comes in. Sorry, no, yeah, basically this arrow, I personally think of it, without getting too much of a sciencey definition, getting myself confused. Basically, we look at the balance of charge, okay? So there's a positive coming in here, proton, and a neutral coming in, out. So if it was on this side, it'd be a positive. But we'll look at this side, where we've got a negative coming in, and we've got electron neutrino going out, okay? So what we need here is it's going to be, because it's acting on the hadrons, okay, we have a gauge boson, okay, and the only gauge bosons we be aware of is the W plus, W minus and Z0 boson. Well, for a start, because the arrow is pointing this way, it's not going to be the Z0 boson, because this is a negative charge coming in and this is a 0 charge going out. Okay, it's not going to be the W plus boson because we've got a negative charge, and if we had a positive charge, basically this exchange particle, I kind of think of it as we're kind of balancing charge. So the charge that goes in must be the charge that goes out, because obviously we've mentioned that in our conservation laws. So we've got a negative charge coming in and a 0 charge going out, so we need a negative exchange particle. Okay, so our negative exchange particle is W minus, so therefore we've got a W minus gauge boson. Okay. Again, 3b part 2, energy and momentum are conserved in this interaction. State two other quantities that must be conserved and show they are conserved. Okay, so again, I mean, you could use these two, but we've got to show that it's conserved. Okay, and maybe the easiest two to show that are conserved, I haven't really mentioned there, but I did mention them in the listing. Okay, so I did say that. Well, let's do charge, because I think that's probably the easiest one to be conserved. Okay, so you remember in the Feynman diagrams, we've got a. This is basically goes in order of time. So we've got this, basically the bottom half of the Feynman diagram. The total charge must equal the top half of the Feynman diagram. That makes some kind of sense. Okay, so therefore obviously we're going to need to do some kind of calculations to prove this is true. Okay, so you could just say before there is a positive, before we've got a positive charge with the proton, okay, and a minus charge with the electron. So overall, going in, so this is before the interaction, we've got a neutral overall charge. And obviously these two particles, the neutron and the electron neutrino, both have a charge of 0, both neutral, so therefore the total charge is also neutral, so therefore the charge going in equals the charge going out, as they are both neutral, so therefore the charge is conserved. And you can go with the baryon number. Well, there's a proton, it's got baryon number of 1, electron, well, it's not baryon, so it's baryon number of 0. The neutron has a baryon number of 1, and the electron neutrino is a also a lepton, so it has a baryon number of 0. Okay, so therefore baryon number of 1 equals going in is equal to baryon number of 1 going out, so therefore the charge and the baryon numbers are conserved. Okay, but as I say, that's just the example, very, very brief example for that. 3b part 4. The exchange particle in this interaction was discovered by an experiment with a rest mass that has been predicted. Why is it important to test by experiment the prediction of a scientific theory? Now, this one really kind of isn't so much a topic that you need to be aware of. It's more of a why do we do experiments question, and I would actually advise, I probably should have put this in my when I went through the spec, that this is kind of a good question to be able to learn, because it's quite one of them questions they might throw in there just to kind of put you off it. And pretty much the answer for this, well, it's a 2-mark question, okay? So it's got to be some kind of detailed answer, okay? So basically the answer is we've got to have evidence to support theory, okay? Or you could say that we have to check that the theory makes sense. In other words, we need experimental data to prove the theory is or is not correct. So any one of them two. And to be honest, for that part, if maybe what I said didn't quite make sense, because I mean, sure as hell didn't to me, the mark scheme does do a pretty good explanation. I mean, normally it's quite shit, but that's quite a good explanation. Okay, so is any more to the 3? No, that's the end of question 3. Thanks for watching, and as I say, hopefully it's been helpful for you, and we'll see you in the next video. Goodbye.